Okay, let's get started. So what we are looking at today is polar coordinates. So up until now, our normal graphing has been in the Cartesian plane, so it's often called the Cartesian coordinate system. But now we're going to look at a different way to move two locations from a polar perspective. So this is all going to be from a trig perspective. So here's our normal way of moving to a point. We start at the origin, and when we were moving to the location 4, 4, that means move to 4 on the x-axis and then move 4 in the y direction. And that puts us at a point in quadrant 1. But if you were actually going to walk to that point, like if you were in a field, you wouldn't walk 4 to the right and then 4 up because that's extra distance. So instead, you would just orient yourself towards the point, and then walk straight there because that's the shortest distance. So polar coordinates represent that idea of getting there quickly rather than moving left and right and then up and down. So when we're looking at polar coordinates, now instead of an x and a y, we're going to have an r coordinate and a theta coordinate. So the theta is going to tell us what direction we're looking at. So when we say 0 degrees, we're going with the same 0 that's on the unit circle. So that is pointing directly right. So to get to this point, I'd turn 45 degrees, and then I'd walk 4 times the square root of 2, which is like something around 6. And that is still shorter than walking 4 plus 4, 8 units. So when we talk about polar coordinates, a point P in the system is represented by the ordered pair r comma theta. So when we write polar coordinates, we always write r first and theta second. Now theta can be represented in degrees or radians. If you're using degrees, you are supposed to write the little degree bubble afterwards. If you use radians, though, you don't write the degree bubble because it's not in degrees. And typically, radians are written in terms of pi. So the big signal that you have a polar coordinate is typically that the second number is written in terms of pi. And that's the tip off that, oh, this isn't xy, this is r theta. But it doesn't have to be that way. Like I could write 5 comma 2, and then it's a question of, well, did I mean the xy point 5, 2? Or do I mean the weird polar point, radius 5, and angle 2 radians? So in general, we're going to write it in terms of radians. So it'll look like these here. A typical example of a polar coordinate system is something like a sonar grid, like you see that gets pinged on a movie, or the weather radar system. Now, it turns out, as far as I can tell in both of those systems, they actually define straight up to be 0 instead of to the right. So in any application of polar, you have to check and figure out where is the 0 mark defined so you can measure your angles appropriately from there. So we're looking at this point A on the grid, and we want to come up with the polar coordinates for this point A. So we see from our radius perspective, the grid now, instead of being a bunch of rectangles, looks like this weird spider web. So we see there's a whole bunch of rings, and then there's a whole bunch of radial lines. So the rings correspond to our radius number. So I see my A point is on the 2 ring, so the radius has to be 2. So that's why all the points have a 2. Now when we look at the angle, point A is on the line for pi over 3, 60 degrees. So to get to this point A, I've rotated 60 degrees, or rotated pi over 3, and then I've moved 2 units in that direction. Now, the radius could also be negative, which is a weird way to work, but there does have to be a meaning for this in the polar coordinate system. So it turns out that a negative radius gets measured in the backwards direction from where you're looking. So you still rotate to your theta, but instead of walking forwards in the direction you're pointing, you walk backwards, whatever your radius is. So I usually associate this with like being in an office chair. So I like rotate to whatever the angle is in the office chair. And then I'm going to like scoot forward the radius, or if it's backwards, then I'll push back that radius. So we're going to see this in action. So if we're looking at the point -4, comma pi over 4, pi over 4 is an angle in quadrant 1. So I started pointing due east, and I've rotated to the 45 degrees, the pi over 4 direction. But instead of moving 4 units positively, I'm going to use move 4 units negatively, which puts me in a location that's actually in quadrant 3. So even though my angle was pointed in quadrant 1, because the radius is negative, I end up backtracking and I'm in quadrant 3. Now we could write an equivalent point for the negative radius here. I could also measure that angle is a full pi radians plus the extra pi over 4. So if I go to 5 pi over 4, now I'm looking in quadrant 3, and then I would move forward 4 units. So this point here could also be written as +4 and 5 pi over 4. But it's equivalent to the original point we started with, -4, comma pi over 4. So we're going to see anytime we're looking at a polar point, there's actually multiple ordered pairs that point to that same location. Now, this is different from our Cartesian or rectangular coordinate system. When I label a point 2, 3, then whenever x is 2 and whenever y is 3, I go to that location, and those two numbers are the only two numbers that get me to that location. In the polar coordinate system, I have an infinite number of points that put us on the same location. And we have the infinite number of points because all of our thetas have an infinite number of coterminal angles. So with my 2 points here, there's actually more than that. I could take my -4, and I have pi over 4 plus any coterminal angle, so plus 2 pi k. On the other side, I could also have 4, 5 pi over 4 plus 2 pi k. So there's actually 2 infinite lists of points that get us to the same location. But that particular location, it has to be either 4 or -4 for the radius, and the angle can't be any angle, but it's either coterminal with pi over 4 or 5 pi over 4, depending on whether we're looking at the positive or the negative radius. So I know that was a whole lot of information at once. What questions do you guys have so far?
Where is the L -4 or 1 -4 coming from?
1 minus 4?
Like the pink? Pink, yeah.
That's a parenthesis.
Oh, okay. My bad.
Yeah, because they're ordered points. The 5 pi over 4 I got by adding, I took my original pi over 4. Oh, and then I added pi, so I was looking in the quadrant 3 direction instead of the quadrant 1 direction. We haven't gone over how to convert between polar and rectangular yet. Now, when we're looking at one polar point to get an equivalent polar point, like that's what's on the next slide. But the idea is any polar point, I can just use a coterminal angle and get an equivalent polar point. Or if I add pi to the angle, I can change the sign of the radius, and that's also an equivalent polar point. So that's what the slide on the next page says. So if I have a polar point r comma theta, I can add or subtract 2 pi k to the theta, and those are going to get me to the same location. Or if I change the sign of the radius, then I add pi to my angle, and then I can go with any coterminal angle from there. So this is like a formula for converting between equivalent polar points. But once you get used to thinking in polar, like you can also just draw a picture and reason through on the picture what you would have to do to get an equivalent point. Now, anytime we have a polar coordinate where the radius is 0, then this is the point, what we normally call the origin. In polar coordinates, we call that location the pole because we're measuring distances from that central region. So on this slide, we're given the original polar coordinate of 3 comma pi over 6. And we want to find other equivalent polar points. So our first one says, keep the radius positive, but make the angle between 2 pi and 4 pi. So that means for my first one, I'm going to take pi over 6, and I'm going to add 2 pi to it. So this will give me an angle that's between 2 pi and 4 pi, but it'll be the same location. So to actually add, we would multiply by 6 over 6. So that is 12 pi over 6 plus pi over 6 gives us 13 pi over 6. So our first coordinate pair, we still have the same radius of 3, comma, and then 13 pi over 6. Now for our next point, they say make the radius negative. So if I make the radius negative, then I take my angle and I add pi to it. So I multiply by 6 over 6, so 6 pi over 6 plus pi over 6 is 7 pi over 6. So I make the radius negative 3, and then my angle is 7 pi over 6. Now, if I also wanted to make the angle negative, I could subtract 2 pi from 7 pi over 6, and I'd get negative 5 pi over 6. That's another way to type the same location, just with slightly different coordinates. Now, our last one wants us to go back to a positive radius. So we're going to keep the 3 the same. So we'll start with 3, comma. And then they want our angle less than 0, but bigger than negative 2 pi. So we're still going to start from pi over 6, but now we're going to subtract 2 pi. So pi over 6 minus 12 pi over 6 is negative 11 pi over 6. So this is part of the question on polar coordinates that we're putting on the test next Monday. Although on the test, what we usually do is we give you an XY point and we ask for a polar point. And then sometimes we've asked for an equivalent point to that point. I don't know which way it's going to be because we're going to meet later today to finalize the test. So what questions do y'all have on the way this played out? How we found the different coordinates for the same location? All right, let's see our next slide. So when we're looking at a polar point versus a rectangular point, if I draw the XY coordinates to get to the same r theta location, I create a right triangle. So in that right triangle, I have my X distance is the horizontal, my Y distance is the vertical, and then my R distance is the diagonal. But that right triangle, when we have theta labeled on the origin, that makes X the adjacent side, and Y the opposite side, and R the hypotenuse. So if I think about my trig functions, then cosine of theta is the adjacent side over the hypotenuse, x over r. And then if I just multiply by r, I get the same formula that we see up in the box, x equals r cosine theta. So if I have a polar point and I want to know what the x coordinate is for that point, I do the radius times the cosine of the given angle. Similarly, but if I use my sine function, sine theta equals y over r, and I multiply by r, then I have y equals r times the sine of theta. So I'm going to give you these two formulas and the other two formulas we'll see later on the test. So you don't have to remember the formula, but you do have to remember how to use them in reference to polar coordinates. So questions on the formulas here. Now, we can plot in Desmos, but it gets a little bit wonky. So one of the first things to know about plotting in Desmos is when you click on the wrench icon for the graphing calculator, there's two different pictures under grid. The first one looks like a mesh and it's a bunch of little squares. This is our normal Cartesian coordinate system. But the spider web or bullseye next to it, that's our polar graphing grid instead. So we see the radius rings and we see the lines with the angles. So if I want to plot a polar point, I can't just type, like we can see here right now, it's set to be a radius of 6 and an angle of 30 degrees. If I type 6 comma 30, it's way up at 30 degrees. Or if I change it to pi over 6, we can see here it's going over 6 and then it's going up the pi over 6 number, which is less than 1. So in order to plot polar points, we have to use our cosine theta, our sine theta for the xy coordinates. But if we go to this slide, you can just type in whatever you want A to be and whatever you want R to be, and it'll calculate it for you and show you where that point is. So we can plot polar points in Desmos. It just requires a little bit of workaround. But we can see here as I slide my radius positive and negative, and as I change my angle, I change where I'm pointing, and then how far along that angle direction I move. So now we're going to try to convert from polar back to rectangular. So this is, since we're converting from polar, this point here is a polar point. So what I like to do on these questions to remind myself and make sure I remember, this is an r theta point. So I just like to, as my first line, say, okay, this is r comma theta. So I can clearly see r is -4, theta is negative pi over 4. Now they're asking for rectangular coordinates, so that means xy. So x equals r cosine theta. R is -4 times the cosine of negative pi over 4. Now, you will have a unit circle chart on the test, so you can look at it and reason through, like, where is negative pi over 4? It's actually in quadrant 4. So negative pi over 4 is coterminal with 7 pi over 4. So we can just use the cosine coordinate for 7 pi over 4, which is positive square root of 2 over 2. But you can also use your calculator to remind you of that. If you type in the cosine of negative pi over 4, make sure you're in radians because this is a radian angle. It'll spit out positive 0.707, or it might actually just type positive square root of 2 over 2 for you. But here, when we're typing this in, like, we know it's the square root of 2 over 2. It's just more a question of, is it positive or is it negative? And you can use the calculator to, like, double check, oh, yeah, the cosine of negative pi over 4 is positive. So this gives us an x coordinate of -2 times the square root of 2. Now our y coordinate, y equals r times the sine of theta. So -4 times the sine of negative pi over 4. Now the sine of negative pi over 4 is negative square root of 2 over 2. So we end up with positive 2 square roots of 2. So negative 2 square root 2, move outside the square root and then hit the comma, positive 2 square root 2. All right, now we're going to plot this point. So we can go back a slide and use Desmos to plot it. So I'm going to type in a radius of negative 4. And I'm going to type in an angle of negative pi over 4. No, that's not right. I have to type in negative 45 then. And this puts our point in quadrant 2. Now, if I think about where negative 45 degrees points, that points down in quadrant 4. But since my radius is negative, I move backwards from quadrant 4, which puts me in quadrant 2. So I'm just going to reiterate that on the graph here. So our angle is negative pi over 4. But then we're moving negative 4. That puts us somewhere about there, where this distance is 4 units, but the negative sign is giving it some direction. Now my xy pair, negative 2 square roots of 2, I go left a number and go up a number, and that gets me to the same location. So what questions do y'all have on this? How we used the formulas for the conversion, and then how we got our picture. All right, now we're going to try things the other way around. We're going to start with rectangular coordinates, and we're going to try to figure out the polar coordinates. So we're starting with some simplified cases. So when we look at quadrantal angles, the xy point for this particular one is 0, 3. And we can see, well, that angle is pi over 2, and the radius is 3 units. So our polar point is 3, pi over 2. So our next slide here summarizes all 4 of the quadrantal angles. Now, I don't recommend memorizing this. I recommend understanding how polar coordinates work and then reasoning through what that location has to be. So here on C, our xy point is negative a, 0. So that means we are left from the origin. So that angle position on the unit circle for straight left is pi, and then the distance we moved left is the absolute value of our x coordinate. Now, this quadrantal angle for the first one, a comma 0, it turns out this is any point along the positive x-axis with a positive radius number, that a comma 0, this is where the x, y, and the r theta points are identical. So that's why when we're looking at these polar versus rectangular problems, they have to tell you whether the ordered pair they gave you is rectangular or polar. All right, so our little graphing activity here, there's a red point, and this is 0, comma 3. And then they want us to shift our x1 and y1 sliders until the blue point meets up on the red point. So when I change my x, I'm just moving the point horizontally. And then when I change my y, I'm moving it vertically. So I set the x coordinate to 0, the y coordinate to 3, and now my 2 points are lined up. So in order to figure out how do I go from the rectangular point to a polar point, I've got to think about my x, y in the diagram here. So I'm going to sketch the right triangle in. So when I have that right triangle and I have all the sides on the right triangle, this follows the Pythagorean theorem. So x squared plus y squared equals r squared. This is the way I will write the formula on the test. I prefer it with r squared because then you write in the square root and then you have to consider, do I want the positive radius or the negative radius? Now, the other thing we need, though, is we need to relate theta to some of these sides. Now, when we look at our x and our y sides, since I'm figuring out starting from rectangular, I want to know which trig function uses the opposite and adjacent. And the trig function that does that, opposite and adjacent, that's our tripping on acid tangent. But the catch here is that tangent, when we're trying to calculate theta, we use inverse tangent, and there's restrictions on inverse tangent. They follow the restrictions that sine of theta has. Inverse sine of theta, or sorry, inverse sine of a quantity is only defined in quadrants 4 and 1. Tangent follows suit. Now we're going to see in our calculation that sometimes the angle we get is going to be in quadrants 1 and 4, but we actually want an angle in quadrant 2 or 3. So we'll take our result from the calculation and we'll add pi to it. So let's go ahead and see this in action. So we're given the rectangular coordinate 2, negative 2. I'm going to plot that on our grid over here. So 2 to the right and then 2 down. So I got to figure out r and theta. So I'm going to start with theta. So we know the tangent of theta is y over x. Y is negative 2, x is 2. And now to figure out what theta is, I'm going to use inverse tangent on both sides. So if I crunch that on the calculator might spit out the radian angle, or I can put it in degree mode and get the degree angle out. So the degree angle will be negative 45 degrees. Which is negative pi over 4. So negative pi over 4 is a quadrant 4 angle. And when we look at our xy point, it's in quadrant 4. So this means when we solve for the radius, we're going to use the positive radius when we square root. So r squared is x squared plus y squared. So x is 2. Y is negative 2. So 2 squared is 4. Negative 2 squared is also 4. So we have 8. And then we square root both sides. So we have plus or minus the square root of 8. So we're going to take the positive square root, but to type the answer in a way that Amplify will be happy, we do have to simplify the square root. So 8 is the same as 4 times 2. I can split the square root across multiplication. So the square root of 4 is 2 on the outside with square root of 2 on the inside. So now I double check. They said where theta is less than 0, my theta is negative, so this is correct. Now then it has a nice little follow-up note. What if instead they said theta is between 0 and 2 pi? Then our negative pi over 4 is too small. So we could add 2 pi to get a coterminal angle. So we used the positive radius because our angle negative pi over 4 is pointing into quadrant 4, which is where our point actually is. So since the direction that we calculated, negative pi over 4, is looking into quadrant 4, and the location of the point actually is in quadrant 4, That's why we're going to use the positive radius. Does that help or no? It's okay to say no. So it would be negative if um if they gave me a point that wasn't in quadrant 1 or 4, if the XY point was in quadrant 2 or 3, if I want to keep the angle I get out of my formula, then I would make my radius negative to move to the correct quadrant. So it just depends on which angle you want to use. That determines whether you want to use the positive or negative radius. So like an equivalent point to our point here, like I could use 3 pi over 4 as my angle, but then I would move backwards for my radius. So that's an equivalent point with a negative radius. And I got 3 pi over 4 by taking negative pi over 4 and adding pi. All right, so this will also help like answer when would we use negative or positive radius. So we're going to look at this point negative 3, 3. So left 3 and then up 3. So we're going to start with our theta formula. So the tangent of theta is y over x. So the inverse tangent of negative 1 is negative pi over 4. So if I keep my angle, yes. So the formula, we want to use the formula that uses y and x. So that's why we keep using tangent theta equals y over x. So we do want to use tangent here because I don't know what the radius is. I could calculate the radius and then I could use any of the trig functions, but like the formula I'll give you on the test, one of the formulas is tangent theta equals y over x. So when we look at the angle we got, negative pi over 4, that's looking down in quadrant 4. But our location point is back in quadrant 2. So if I'm going to keep my angle the same, then I have to use a negative radius to end up in quadrant 2. So we have x squared plus y squared equals r squared. So negative 3 squared plus 3 squared equals r squared. So that's 9 plus 9, which is 18. Now we square root both sides. So to get our initial point, we're going to go with the negative radius. And then 18 is 9 times 2, so it'll be negative 3 times the square root of 2. All right, the other thing we can do, since it didn't like my 2 negative results, so if I take my negative pi over 4 and I add pi, I get another angle of 3 pi over 4. But if I use 3 pi over 4 for my angle, then I'd use the positive radius, which is positive 3 square roots of 2. So the answers are equivalent. Amplify was just taking one of the answers over the other, but it truly doesn't matter. Now, WebWork will be more explicit. They will tell you, write an answer where the radius is strictly positive. So we added pi because we were trying to figure out like what's an equivalent point, but not using all negatives. So instead of looking at negative pi over 4 and scooting backwards the distance of 3 square roots of 2, if I want to figure out what is it if I was going to scoot positively, I add pi to the negative pi over 4, and that gives me the angle of 3 pi over 4. But when I make that add pi change, I also change the sign of the radius. Now, what we're going to see next is we're going to start looking at graphing these ridiculous equations. You're not going to have to graph one of those equations on the test. I just want you to be roughly familiar with how the graphing works, but we are going to mess around with converting the equations.